We've all seen balls roll down a hill or an incline, but why does a round object roll rather than just sliding like a block? Well, some of you might automatically say friction. Some of you may say that gravity is what's causing it to happen. And actually, you're both right. It depends on which perspective you want to take. If we think about the effects of gravity, gravity causes a torque about the contact point that's been labeled here with a red dot, and that causes that sphere to turn or to roll. Another way of thinking about it is that friction exerts a torque about the center of the ball, and that is what causes it to roll. So there's sort of two ways of thinking about it. We're going to start with this method here. It is the more traditional way of approaching this question, with friction exerting a torque and thinking very clearly about the two types of motion in this situation, the linear motion and the rotational motion. All right, so let's consider this specific situation, a sphere rolling down an incline, released from rest or pushed, it really doesn't matter. We are just going to look for the acceleration rate as it moves down the incline. Now notice this problem says, what's the acceleration at the bottom? Again, that really doesn't matter. The acceleration would be the same at all points along the incline. The other important idea that's mentioned is that it rolls without slipping, and we'll see in a few minutes how that will be incorporated. Let's begin by labeling the forces on our sphere. We would have gravity, of course, pulling from the very center of the object. We would have a normal force because the object, the sphere, is in contact with a surface. And then also because of that surface contact, we would assume there is friction. Now, why do we assume there's friction? If there was no friction, the sphere would have a tendency to slide down the incline. And so because we know it rolls without slipping, we would have to definitely include that frictional force within our ideas. This also gives us the direction of the frictional force. If there was no friction, it would tend to slide down. Therefore, friction must point up the incline. But what type of friction do we have here? Well, turns out that this friction is actually static friction, which is a little confusing because obviously the object is moving, and so it seems as though kinetic friction would be used. However, the actual point of contact is not moving at any particular instant. Let's investigate this a little bit. First, take a look at this picture. This shows a wheel that is rolling without slipping, and you can see how at the top of the wheel up here, the spokes are very blurry. That's because they are moving faster than the other points on the wheel. The points down here, the spokes down here, are actually fairly clear. And if we could see the exact bottom point of this tire, it is not moving at this particular instant. That's going to be the key idea for why we will use static friction instead of kinetic friction. Let's break this motion into two parts. First, let's assume that there is no friction, and so our wheel or our rotating object slides. In this case, every point on that wheel would move forward at the exact same speed, which we'll call v. If instead we think about just the rotational part of the motion, so imagine that it doesn't slide, but just spins about its center of mass, then we would have to talk about the tangential speed, or the linear speed at a particular point. And in that case, we would use the formula v equals r times omega to represent that speed. If the object rolls, then it has both types of these motions. If it slips as it rolls, there is no specific connection or relationship between the v for translation and the v sub t for rotation. And we would use kinetic friction in this case. The wheel would be slipping, and so that would be a kinetic idea. However, if we have the special case where the wheel rolls without slipping, then the v from the translation picture and the v sub t from the rotation picture are the exact same v's. And then it's kind of interesting because here at the top of the wheel, the V's are pointing in the same direction. And so if they're equal, the speed of that top part of the wheel is equal to twice the V of the wheel as a whole. At the middle point, the center of mass is moving forward based on translation or linear motion, and it's not moving based on the rotational. It is the axis point. And so the center does move forward at V. But here's the real key point. The translational motion is pushing the wheel forward to the right. The rotational motion is pushing it backwards to the left at this point. And so instantaneously there is no speed right at the bottom point. And that's what we mean by not slipping. What that allows us to do then is to say that the friction at that point is static friction because that particular point has no velocity relative to the ground. All right, so how do we do this problem? We're going to break this into linear motion and rotational motion. Let's start with the F equals ma equation. We will begin by putting in our downward or down the incline force, which is the component of weight, mg sine, and then subtracting the frictional force. And again, that's going to be a static frictional force. Where are we going to get that static frictional force? Well, we don't have a specific value. Even if we had been given a mu sub s, that wouldn't be enough because we aren't necessarily at the point of breaking free. There is just some amount of static friction, enough to keep things rolling. So we'll turn our attention now to the rotational motion, and we'll use the fact that torque equals I times alpha. The force about the center point is the frictional force. Notice I'm not including the normal force here because the normal force runs right through our center of mass point, and I'm not using the weight because that runs right through the center of mass point. So again, I'm using the center of mass point as my reference here. The angle between friction and R is always going to be 90 degrees based on the way the contact is. So I don't need to worry about the sine of theta. And I, for this particular object, is 2/5 mr squared. That's because we were told it is a solid sphere. So that's something that will change based on the description. So that I can make a connection between my linear and rotational motion, I will make a substitution for alpha. Recall that A is equal to R times alpha. So alpha equals A over R. We made this kind of substitution before when we worked with real pulleys. Right, continuing on, we can notice that there are some things that cancel. There are R's on both sides of the equation and on the top and bottom of the fraction that can be removed. And so now we have an expression for the frictional force, which we will substitute over to the other side. Again, we can notice some things will cancel. M is now in every part of our problem. And we can do a little algebra, bringing all of our A terms to one side and combining those like terms so that they are 2/5 plus 5/5 is 7/5. Solving for A, we get 5/7 g times the sine of theta. Now, as mentioned before, this problem can be solved using a different method. If you'd like to see that, check out the second video.